We're going to start with this first topic, tree worker safety. Once we get into this, we'll take about a 5-minute break after the safety session, and then we will get into climbing. And then we'll finish up today with risk assessments. So if you have questions, I'll see if they show up while I'm presenting. And if they do, I can stop and answer them, of course. All right. We've talked about before, we talked about the ANSI as it came to pruning standards. Today, we're going to talk about ANSI in terms of safety standards. In the American National Standards Institute, we fall under the jurisdiction of forestry. Forestry operations are governed by Z133. These were updated in 2017. So whenever you see this, let me get a laser going. So whenever you see a dash with a year after it, that'll be the year that the original was updated. We're going to talk about personal protective equipment and work zone procedures, potential hazards near electrical conductors, and we'll get into the minimum approach distances you can do with that. Chainsaw and chipper operations and procedures. So I know that we have some people in this class that are taking the class for CEUs, and we also have some people in the class that have no idea about safety or climbing or risk assessments, things like that. So keep in mind that this is a sort of the entry-level exam, and I know you guys have done some more advanced things than this, but for the purposes of the exam, we're going to stick to the material today. Not only are we going to talk about ANSI, but ANSI is not an enforcing body. ANSI just sets the actual standards. This is the legit way to do it. However, there is an enforcement section of the government, and this is the Occupational Safety and Health Administration that you might know as OSHA, and it was brought about through the Occupational Safety and Health Act. The purpose of OSHA is to reduce occupational injuries, illness, or death through the establishment and enforcement of safety standards and regulations and the provisions for mandatory training. OSHA has established many regulations that affect arboricultural work. So OSHA that governs tree care often is cobbled together from several different industries, so they didn't have to rewrite the whole standard. So you might see things like this ANSI Z133, and then somewhere else you're going to see a different standard number, and it might have come from a different industry, but it still pertains to us. So the Z133s, this is the set of standards for arboricultural operations approved by the American National Standards Institute. It is intended to provide safety standards for workers engaged in pruning, repairing, maintaining, or removing trees or cutting brush. It's important that all tree care workers be familiar with and comply with the Z133 2017 standards and all applicable OSHA regulations. For those of you that have tailgate safety sessions, there are safety sessions specific to the ANSI Z133s. So I would encourage you to go over those things, have copies of them, and put them into your training notebooks, especially for all your new hires that might not have heard it during a tailgate safety session, so that they can become familiar with it. There's some very specific terminology that we'll use. One of the words is approved, and this means that it's acceptable to the federal, state, provincial, or local enforcing authority having jurisdiction where it's used. Approved only appears on equipment. So you might have an approved hard hat, approved safety goggles, approved climbing saws, things like that have the word approved on them. Shall and should are two others that you'll see pervasively throughout the documents. Shall denotes a mandatory requirement that OSHA has law enforcement privileges. You shall wear closed-toed shoes appropriate for the job. You shall, so wherever you see the word shall, it means it's mandatory and it's a law. And so you can be held liable for not following the law. You can be fined, you can be jailed, all that sort of thing, if someone were to turn you in. Another word that you might see pop up a lot would be the word should, and this denotes an advisory recommendation. They don't want to have to get down into the specifics, so they might say wear long pants. But if you're on the ground, those long pants might incorporate saw chaps. If you're in the tree, they might be stretchy kind of pants where you can move around, but they have to be long pants. So they use the word should to give it a little bit broader meaning, but you should still take it very seriously and apply it to the spirit of the law, so that you guys are staying as safe as possible. You'll also see the word PPE out there quite often. This is the personal protective equipment. Employers shall require employees to wear clothing and footwear appropriate for the work conditions. Again, this is a little vague, so what the plant healthcare operator might don in the morning would be different from what the climber might wear, which might be different from the brush dragger and might be different from the sales guy that went out and saw the job. But there is appropriate wear for all of those people. All employees shall wear eye protection approved by the ANSI Z87.1, updated in 2010. Hearing protection if sound levels are expected to be above 8 hours at 85 dB on a time-weighted average, TWA, and a helmet that's approved. This is the Z89.1. So the Z89.1 comes about from the mining industry when people first, most of the head injuries came from standing up too quick in a mine or getting hit in the head with a post, something like that. So they started mandating these approved hard hats. We'll talk a little more about the time-weighted average thing in a minute, I believe. Here's some examples of personal protective equipment. On the ground, we see that you might use these saw chaps if they're not built into your pants. We have sturdy closed-toed shoes. We have a chainsaw that looks like it has an operational chain brake on it. Its safety features are still in place. As I was saying, the saw looks like it's intact. It has all of its safety features in place, it looks like. The hard hat over here has some earmuffs on the side for hearing protection. It has a screen on the front for additional protection. So jewelry should not be worn because it may catch in the equipment, especially anything that dangles around. If you have earrings, replace them with studs. If you have nose rings, take them out. That sort of thing. Anything that has a loop in it that can be caught by brush when you're feeding it into the chipper, or if you're up working in a tree, that sort of thing. So this is a should not be worn. So this is an advisory statement. All tree workers shall wear head protection that is in compliance with ANSI Z89.1. So this is a shell. So anyone involved in tree care operations, that means if your sales guy's out there walking around on your site, he has to wear a hard hat. If your plant healthcare guy's working there at the same time you're doing aerial tree work, he has to wear one, but it might not be the same hard hat he would wear if he was on a job site by himself. So it still has to be approved, and it'll be stamped on the inside of the hard hat somewhere. Eye protection shall be worn when performing tree work. So tree work's pretty all-inclusive. So you might have, that includes chipping, it includes climbing, dragging brush, all that sort of thing, walking through the woods, all that's considered tree work. So back to the hearing protection. So this is required for all workers that are exposed to loud equipment for prolonged periods of time. So hearing loss is cumulative. It's something that builds up over the course of the day. So you have these long sustained periods of a lot of noise. Think chippers make an extreme amount of noise. So if you're exposed to that for a long period of time, make sure that you are wearing hearing protection. A lot of the larger companies out there send all their guys to get a hearing test when they're hired so that they get a baseline of how good their hearing is. And then they test them every year and look for things like hearing loss to see if people really are wearing their ear protection, their hearing protection or not. So either the muffs like these or something similar is good to wear. So it looks like, okay. So gloves are strongly recommended for certain jobs. I'm just going to check to make sure everything's still doing what it's supposed to do here. Yeah, so gloves are strongly recommended for certain types of operations, such as sharpening chainsaws and chipping brush. And you've probably seen those kind of gloves that have the gauntlet on them. The gauntlet style gloves are not to be used because it's a big open cuff, so branches and things like that can get inside of it and drag you into the chipper, which I assure you is something you do not want to have happen. All tree workers should wear sturdy boots approved by the employer and appropriate for the work being completed. Again, if you're around the logs and you're climbing the trees and all that sort of stuff, very sturdy footwear. If you're on a plant healthcare crew, something like that, then you might just want to wear waterproof boots. So it'll be different depending on what the application is. Leg protection must be worn when using a chainsaw on the ground. Chaps or chainsaw pants are designed to jam or slow the saw chain. So these pants are filled with Kevlar fibers, and as soon as the chain picks up on any of those fibers, it pulls it into the saw and throws it into the clutch and jams the saw up so that the saw does not move. The new electric saws have been designed to also work with the same material. A good friend of mine, his name is Andrew Machuca. He is one of the best climbers in the world. He's gone to nationals many times. He's one of these guys, he's a serial competitor. So he travels around the country participating in these championship climbs, but he's also just a regular tree guy. So this is Andrew up climbing a tree. He's got on his safety equipment. He's got on his saw chaps. It looks like might have, I guess you guys can see the top of the picture. So up in the top of the picture, you can see that he's got his hard hat on. He's using his chainsaw appropriately and to chest level, that sort of thing. He's got a guy in the background who's wearing his hard hat. This guy's running the lowering device, so he's got everything he needs here to be in the know. So if you can find Andrew on Facebook and Instagram, all that sort of stuff at Above It All Tree Care. For me to be able to use his pictures and stuff like that, I agreed to plug his Instagram. So the other thing that a job site needs is good communication. Good communication among workers is an integral part of working safely. Each worker on the crew must be aware of what the others are doing, and each must take measures to prevent accidents. There must be a clear and efficient means of communication between climbers and ground workers. Now you saw Andrew's head setup or headgear up here. This is one of those helmets that has the built-in noise cancellation, and it also has Bluetooth connectivity so that he can speak to all of his other employees that are on the job site at the same time. But it doesn't have to be that sophisticated. It can be just a clear language that everyone uses and expects. And this is such a good way to get your team to work together. Everyone's eyes, everyone's ears, and everyone's speech can play a part in safety. Even the guy that just started today, because maybe he sees something, an electrical hazard that no one else saw, or he might ask questions that makes other people stop and think, maybe I should go back and look at that. So everyone's voice has some meaning and can help make a safe work site. So when you're creating your working area, you designate things like landing zones and drop zones. Everyone needs to know what's going to happen and where it's going to happen on the job site, all of your employees. So the landing zone is a predetermined area where cut branches will be brought down in a rigging operation. So think of landing zone like an airplane. It's a very controlled, and you've got a very specific area that you're going to land the airplane. Same sort of thing with heavy duty brush or large logs. You're going to lower them down gently to the ground using ropes. But that's not the only way to get things to the ground. So you can also just drop them out of the tree. So the drop zone is the area where cut branches will or could be dropped from the tree by workers aloft involved in tree care operations. So the difference here, the landing zone is controlled because it's part of a rigging operation. Rigging means that there's a rope attached to it. And then the drop zone is you're just going to put the logs in the same place each time. So we talked about some clear signals. This is called the command and response system. This ensures that everyone knows what's going on and everyone knows to either look up, check on the climber, see if he's got a log in his hand ready to drop it. But examples might be that the climber has popped his log off, he's ready to put it down in the drop zone. And so he's going to yell out something like stand clear or headache or pay attention, something, but it needs to be consistent throughout your company. You can write these things down so that you have a written command and response system in place for your company. And then you wait to be acknowledged. So after you say stand clear, the people on the ground are going to say something back like all clear, like you're good to go. If you've ever been a climber in the woods with vines growing everywhere, there are times when you've got a big cut log or something and you can't see the ground. You can't see who's down there because your vision's blocked. So this is extremely important. Hand signals can be used as well. There are people that cannot hear who do tree work, so feel free to create some sort of command and response using hand signals. Then there's two-way radios, and now we have full communication with Bluetooth. Each job should begin with a job briefing. This coordinates the activities of every worker. It's usually a fairly brief meeting of the tree crew at the start of every job to communicate the work plan, what everyone's responsibilities are, what you're going to require of them, and to identify potential hazards on the job site. The work plan is a predetermined orderly means for getting the job done. So this is the briefing up here includes the work plan, whatever. So this could be stuff from this is where you're going to park the truck, and this is the guy that's going to drive it to the dump when it gets full and come back, or two guys, or whatever it's going to be. You're also going to identify what the work is. Okay, we're doing one tree in the front yard, we're doing one tree in the backyard. So-and-so is going to climb this one, and so-and-so is going to climb that one. You're going to be their groundman, you're going to be their groundman, and oh yeah, the guy in the front also needs someone to run the rope, so you're going to send not only a brush dragger, but someone that can help in the rigging. And then you're going to distribute the equipment as necessary. You're going to make sure that you're filling your chainsaws on top of a tarp. And this is where the tarp's going to be. This is where we're going to store the saws when we're not using them, all that sort of stuff. General safety at the site begins with proper training. All workers must be adequately trained for their work requirements, and this has to be documented. Safe work procedures must be established. If you have a guy that's dragging brush, you need to have a written plan that says this is how we identify the guy dragging brush. He needs to be able to accumulate the brush as it falls down and put the butts all in one direction. Don't exceed some weight or whatever in your branch bundle. You're not allowed to operate chainsaws. All you're doing is dragging brush. Make sure that when you're dragging brush, you're not pulling the climber's line or the rigging line or damaging the yards or whatever. It just needs to be written down. And then that's all that guy's allowed to do until you train him to do something else. So his next level might be running a ground saw. So he'd have to know how to properly wear the chaps, how to properly start and run the chainsaw, how to operate the chainsaw as far as cutting or bucking logs or branches, things like that. All this needs to be documented each time you do it. And then at some point, he might become the chipper operator. And then after you've done brush dragging, ground saw operations, and chipper operations, you might start that guy on rigging operations to be the groundman as a rigger. And then you might start him climbing. So there needs to be an established written training program that documents when this training occurred and what the training was. It's also recommended that all workers receive training in CPR and first aid. An adequately stocked first aid kit shall be provided on each truck. Here's that shall word over here. Now it says adequately stocked, so this changes depending on what kind of truck it is. Classifications of first aid kits designating the assortment of items and quantity of each item is based on the anticipated number of users. If you typically have a 3-man crew, then you need to base it around a 3-man crew. If you have 5-man crews that are running out there, it needs to be based off of a 5-man crew. It's intended to be served by each first aid kit as well as the complexity of the work environment and level of the hazard. So the sales guy, he might only have one of those little cheap first aid kits that has Band-Aids and tweezers and things like that in it. Your plant healthcare operator might have the next level up that might have industrial size eye wash bottles in it in case he gets chemicals in his eyes. It might have a change of clothing in it, like one of those zip up Tyvek suits in case he gets chemicals on his own suit. Things like that would be on that PHC truck. If you have a bucket truck incorporating a chip body and you're carrying a big chipper and you've got 5 guys out there on the crew, that's when you want to step up to things like first responders type level of first aid kits. So make sure that it's your first aid kit's appropriate. Emergency phone numbers should be posted in the truck. Now we've gone to using our cell phones for work orders, or you might have a tablet or something like that. Some people still write them down, but make sure that it's available to the people on the ground. If you're the climber and you're up in the tree and you have an accident, you get stuck in the tree or you get knocked out, someone on the ground needs to be able to know what address where you're located, and know how to go out and stand at the end of the street on the phone talking to 911. But they're not going to know where they are if your phone's locked up and they can't open up the work order. If you don't want to give out your phone number, make sure that you have the address, the property address where you're working somewhere in the truck for people to find and know that 911 should be called. Plant healthcare operators might also want to put poison control in their trucks as well as the local hazmat in case you have a spill. All crew members should be trained in emergency response and aerial rescue. Now, does that mean that all crew members should be able to climb up a tree and rescue a climber? No, that's not what this is saying, but there is a role to be played by everyone on your team. One role might be calling 911, waiting at the end of the driveway for the ambulance or the first responders to show up. Or it could be your number 2 guy on the team who's a climber and he needs to learn how to be able to identify electrical hazards and eliminate those before going up to rescue you. Or if it's a pretty straightforward job without that involved, he can climb up there and actually rescue you as the primary climber. All climbers should be trained and capable of carrying out an aerial rescue. And it's highly recommended you practice this at least once a year. Most companies try to practice aerial rescues once a quarter. It is a cumbersome thing. These use a full-size rescue dummy. These things are 150, 160 pounds, and there's nothing like the experience of rescuing something that heavy that's incapable of its own movement and getting them out of a tree safely. We used to use a combination of I would climb up the tree and pretend like I was hurt, and someone would have to come up and get me out. And my tendency was always to push away from a branch or do this as we were coming down to make it easier on the guy rescuing me. But the real dummies aren't so forgiving. A second climber that maintains line of sight with the aloft climber should be there to carry out an aerial rescue. So this is a should, it's not a shall, but it is strongly recommended that you have a second climber on each job. Traffic control is a big issue in our industry. Anyone that's ever pruned a tree over a sidewalk, you can put up cones, you can put up flags, you can put up tape and all kinds of stuff saying this is a work zone, and people will still just pick it up and walk over it and walk right through your work zone, or they'll drive right through it even if you have somebody out there trying to stop traffic. It drives us crazy. But you are responsible if someone gets hurt inside of your work zone, even though they picked up the tape and walked underneath it, you're still liable if they get hurt. So take this as a legal responsibility of the crew and ensure that you're properly performing that job task. If you're working on something like a college campus or a busy downtown street, I would strongly suggest hiring a company. There are companies that this is all they do, and they have certified crews that can manage pedestrian and vehicular traffic. So on to some electrical stuff. Electrical conductor. This is any overhead or underground electrical device, including wires, cables, lines, and related components and facilities capable of carrying current. It doesn't mean that it does carry current. It means that it's capable of carrying current. So if you have a telephone pole with a guy line on it, that guy line can be considered an electrical conductor. An electrical hazard exists when a tree worker or any conductive object comes within the minimum approach distance in feet of an energized conductor. The absolute minimum, regardless of how much potential voltage or current is there, is 10 feet. On the higher the voltage, the higher the potential current, and the power on a telephone pole is current because there's somebody always using it. So voltage, remember, is just a potential difference. Current is what you get when you use it. So you think about water moving through the hose. So the greater the potential for the current, the greater the voltage, the greater the distance this MAD becomes. MAD can become much more than 10 feet. Direct contact of a body part with an energized conductor. This is where you're actually touching an active wire. So it's either on your hand or you have a branch in your hand and the branch is too heavy and it's pulling your hand down, and it catches you or it pulls you down onto the energized conductor. That is direct contact. Indirect contact of a body part with conductive tools, tree branches, trucks, equipment, that sort of thing. So if we went back to that same example of it pulled my arm down onto the conductor, instead of my arm, if the branch itself falls on the conductor and completes the circuit, then that's indirect contact. Or if I'm using a pole pruner and my pole pruner gets stuck in the part and it pulled down onto the conductive cable and then travels back down the pole pruner to me, that's indirect contact. So chainsaw safety, you have to wear work boots, a hard hat, hearing protection, eye protection, saw chaps when working on the ground. So how many times have you driven by a tree care work site and you've seen a guy out there in a sleeveless shirt wearing shorts and worn out tennis shoes? That stuff is just not acceptable out there. These things are all requirements on the ground. These are all shells. It's important to understand reactive forces of the chainsaw. Remember, for every action, there is an equal and opposite reaction. So reactive forces is what that's trying to explain. So if you think about shooting a gun, maybe you see the recoil in your hand. So the bullet leaves out of one end and pushes back against the gun, which is that pushback against the gun is what you feel as a reactive force. So it's the amount that the gun has to absorb is equal to the amount of the bullet going out. So on a chainsaw, we'll show some examples in a minute, but on a chainsaw, the chain spins around at very high velocity. It has a good deal of mass. And so either the chain spins or the motor spins around the chain, right? Or you could think about an airplane propeller, where if you could reach up and stop the propeller with your hands, the airplane would spin around as long as the engine stayed running. So that is a reactive force. Use the chainsaw with two hands, control the saw. Be aware of the people around you. We tend to get hyper focused on what we're doing as soon as we start a chainsaw. So make sure that you know what's going on around you. Engage the chain brake when walking or repositioning over just a few steps. Chainsaws are much easier to start now. They're solid state ignitions and stuff like that. So maybe it's better just to turn them off anytime you're going to walk away from your work area with the saw. So kickback, the easiest way to think about it. So if you thought about the airplane propeller again, where I'm stopping the propeller and the airplane has to start turning, that moment when I stop the propeller and the plane starts moving, that's what kickback is. So that's when the chain stops moving for an instant and the force is transferred around the gearing and the sprocket of the chainsaw, and the saw wants to come back and hit you in the face. Kickback occurs many times faster than a human can react. Chainsaws require no license and no training to own or operate as an individual. If you're on a tree care crew, remember you have to have documented training before you're allowed to operate it. But just in general, chainsaws require no license, no training to own or operate. Approximately 28,000 injuries or deaths are reported annually in the United States. So this does change over time. So this used to be a really significant injury in our industry. It used to be chainsaw accidents were like number one, number two, go back and forth. However, now because the saws have become so safe, it's dropped down in relevance. So here I've just listed off, I think this was from last year in our industry, the number one injury was created by falls. So people that fell out of the tree or fell off of their rigging, that sort of thing. Struck by, these are when a log or a branch hits you. And this can include things like widowmakers for the climbers. So there might be a dead hanging branch above you, you're climbing up, it dislodges and hits you. That's a struck by. And number third is electrocution, where the victim violated the minimum approach distance and made contact through a tool or directly. So here's some more chainsaw diagrams to help us understand what's going on. Let's see if I can switch to a pin here, see if that'll work for me. So inside of this cover, there's a little sprocket. On the outside, this chain moves in this direction. And it goes around the end of the bar. And so on the top of the bar, the chain's moving away from you. On the bottom of the bar, the chain is moving towards you. So you're going to have to put your theoretical hat on here for just a second. Even though this is not theory, this is truly what happens, but it's so instantaneous, we never realize it. So at some point, there is a transition here where the chain transitions from going away from you to where the chain comes back towards you, the operator. And that's this point right at the tip of the saw. And so at that tip of the saw, that's the easiest place to stop the chain because it's already instantaneously stopping and starting at that one point on the entire loop of the chain. It's right there at that one point at the tip of the saw. So that's when you're cutting through something, even though you might be focusing on cutting this log, you might not have paid attention and there was another smaller log out here that catches the tip. So as soon as that tip gets caught and it stops, the force gets thrown into the chainsaw. So the chainsaw is going to be thrown back up into your face because you have one hand here and you have one hand on the crossbar. And so it's going to pivot inside of your forearm, and the chain brake hopefully will hit your forearm stopping the chain, but the momentum's already been done. These things are very powerful. They can throw back in your face very quickly, but everything operates quickly. So if everything is done correctly, you might only just get hit in the face. You might not get cut. So if you're wearing your hard hat and you're not wearing it backwards, but you're wearing it with a little bill out front, the chainsaw is designed to hit that and fold your hard hat up in the air, which will protect your face. And it also, as it rotates around, will activate the chain brake and stop the chain from spinning. So it's not going to cut into your face or the hard hat. It might just be a blunt injury. There are some other instances where you can accidentally hit this tip. So when you're starting to cut and you can't really see where you're starting, make sure that you're either on top of the chain or on the bottom of the chain and you're not working around this nose of the bar. The more you practice chainsaw use, the better you will get at identifying when kickback occurs, because it will occur to you. It occurs to everybody at some point, but learn how to control it and be safe with it. But avoid using that nose of the saw until you have a good understanding of these reactive forces. Another place might be when it's hidden. So this might be a big tree trunk and you're making your final cut down here for the stump, and your bar is not long enough to go through the whole diameter. So you might have to do a little bit and walk around the tree and do a little bit more and do a little bit more until finally you've sawn through the whole stump. But in this example, you can see where he's rotating it blindly. He might be moving it like this, trying to clear the chain or clear a bind or something, and then he or she could easily hit this nose up here and get kicked back. So felling safety. Workers that are not directly involved in felling a tree should be at least 2 tree lengths away. So get the heck out of there. We don't need you around. Just isolate it to the people that are trained to do the tasks. Workers directly involved in tree felling but not operating the chainsaw shall be 1.5 tree lengths away. You can have a cascading effect. The tree that you're working on can fall into another tree that falls into another tree that can drop on you. So that's why you're 1.5 times the tree length away. You could also have dead branches hanging up in trees that you're not even working on, but when you drop the one tree, it can hit the tree that your rope guys are under, which would allow that branch to fall out, maybe hit somebody. So that's why you want to be this 1.5 feet away. The guy that's doing, well, everyone out there should have an escape route planned, especially the guy working on the tree. So he needs to think about a 45-degree angle away from the line, the intended line of the fall. So make sure that when you're running away, the tree's not chasing you behind you. And make sure your path is unobstructed. You might need to take rope and move bushes away, or if it's in the woods, you might want to cut a free path of branches and blackberry vines and all that sort of stuff so that you can run away from the tree effectively. So here's some other vocabulary words. A tagline, this is a pull line for added control. This is a line that's tied directly to the tree in one space, and it comes down into the hands of the people pulling it or the machine that's pulling it. The retreat path we just talked about, this is your escape plan. Felling notches and bark cuts must be made high enough above ground level to enable the chainsaw operator to cut safely with a stable stance. You saw in the previous slide, you see the amount of stump here. This means that he's not down on his knees making this final cut. He is more upright. He's in a position where he can take off and make that run. So felling notches, these are the sort of wedge-shaped pieces that you see that are cut into the trunk of the tree, and is the first part of the actual felling operation. These notches do have a very specific function, and each notch type has a good use for it. So we have an open face notch, we have a conventional notch, and a Humboldt notch. All of these are fairly common notches. There are other types out there that more advanced tree felling techniques that are used. However, keep in mind this particular exam is going to focus on these 3 types of notches. So an open face notch is going to be it's going to look like a Pac-Man. It's open like this. The conventional notch is going to look like this. And the Humboldt notch is going to look like this, upside down. I don't know if my video is working, so I'm going to draw these on here because I can no longer see myself.
I can see you, Rob.
Okay. If we thought about our tree over here like this, you might have a notch that comes in. I don't know why it keeps drawing those horizontal lines like that. It looks like that. So this is the open face notch. If I had the same sort of setup here and just came down and it was flat here, that would be the conventional notch. And then you turn this conventional notch upside down, and that's the Humboldt notch. So the reason that they have these different types of notches, this one is now much more commonly used because you have control of the tree as it comes down. So you have what's called a back cut, and that back cut is going to start from the back side of the tree and go towards the apex of this notch. You're only going toward, not the apex, but the focal point of the back side of that notch. So these other ones, you're not shooting for the bottom of this base. You're shooting for a little bit higher, so somewhere in here. But on the open face notch, you want to shoot for that point in the back. So if the tree will start to fail when you're in here somewhere, so the distance between the actual back of the notch and where the tree starts to fall, this creates what's called holding wood. And we'll look at holding wood in a minute. The open face notch should be about 70 degrees, and it allows the tree to hinge longer. If you think about the sort of wedge shape like this, and it's closing, it'll continue to stay attached to the trunk without popping off of the trunk for that full 70 degrees of motion. If it's a 45 degree and you have a 45-degree notch, so it's going to come down and hit the top of that notch onto the bed cut, and it's going to break off and it'll pop and move. So you lose control after it comes off of the stump. When it's no longer attached to the holding wood, you lose control of the situation. So that's why these have become this open face has become a much safer way to do these. Barber chair results when the trunk is split upwards from the back cut. You might have all seen that Facebook video where the guy's out in the woods sawing down like a big redwood, and then the redwood starts to just pop apart and pieces are flying all over the place. That's a barber chair. It usually happens when you're felling a tree that's on an angle. So if the tree's not up and down, but it's at a slight angle, think about the dynamic forces here. You have compression on this side of the trunk because it's pushing back towards the ground. It's compressing towards the ground. The back side of the tree is under great tension. So if I make my face notch over here, it's not going to have much impact. This is the compression side. Remember, most of the strength is in the tension side. So as I start to cut, there's going to be a tendency for it to want to split open as I cut through this part. It'll pop open because it's under so much tension. So if you've ever seen the old cartoons where they have the handle that jacks the guy up in the air and you let that handle go, it'll do this on its own and the chair will come down. And that used to hit people in the leg or the face and things like that. So that's where the term barber chair came from, and the action that you think about when it happens. Felling wedges. So if I'm cutting into the backside, my tree's not moving very much, and this is a big tree, I can put in a plastic or aluminum wedge here into the backside of the tree and strike it in with a mallet or a sledgehammer or something. And that wedge is going to open that cut up, and as it opens up the cut, the tree will fall over. These are typically made out of plastic or aluminum. It will be something softer than the chain of your chainsaw so that you don't damage your chain or damage yourself as the operator. So again, the standard or the common notch is the 45-degree opening with the cut above the horizontal cut. The Humboldt is a 45-degree opening with the cutout below the horizontal cut. Humboldts are typically used in the forestry industry to save as much wood or as much trunk as you can, so you can uh, sell more board feet of it, so you're going to get more timber that way. The open face is now the most used. The notch to be cut out is about 70 degrees. This notch has the greatest amount of control. Holding wood should be 10% of the tree's diameter. So if you remember back to here, if this tree were 10 inches from here to here, then I need at least 1 inch between where I stop cutting and the back of the notch. So again, you want 10% there. Some equipment. Brush chippers are very dangerous, requires proper training and safety work practices. Make sure that if you have someone operating a chipper, that person has been trained on its operations and understands its limitations. Can I take my T300 and pick up a 20-inch log and jam it into the mouth of a 19-inch chipper? That's not going to work very well. It could create all kinds of problems. So there are limitations to the equipment we use. I used to have a guy that came to these sessions all the time, and he got caught in a chipper and actually lost most of one leg. And I would get him to stand up and talk about the dangers of running chippers. These things are just incredibly fast, and it's incredibly important that your crews be trained on how these things work. He'd actually seen as he got caught by the brush that he was going to go into the chipper. But so did his crew guys, and his crew guys went over and grabbed him like this and tried to pull him away. But when they grabbed him like that, they held his arms so that he couldn't reach up and hit the reverse bar. But once he actually started going into the infeed rollers, the guys got scared and let him go. And he had the presence of mind to grab the last chance cables hanging down inside of the chipper and managed to reverse it. So he saved his own life, but not before he saw his foot go through the chipper and wind up in the chip box. Training. Proper PPE. This is no loose clothing or jewelry. Don't let the climber come up with his harness and his rope still attached and try to get in there and do brush, because the brush can get caught in all of his equipment and pull him in to the chipper. Aerial lift operators must be properly trained on how to inspect their equipment. The proper PPEs for the operation of that equipment, because they'll be different for that of the climber. And you'll have this fall protection stuff involved. Emergency lowering procedures. There are ways that if the engine dies or the pony motor dies, to still get the equipment back down to the ground. But there has to be people on your job site that know how to bleed these valves off to get you back down to the ground safely. You can also do aerial rescues of people in buckets, as well as in trees. So if you have bucket trucks in your operation, make sure that you're practicing aerial rescue to get people out of the bucket as well. Be familiar with the capabilities and limitations of your equipment. Just for instance, if you're operating a crane, they'll have a minimum or maximum angle of the terrain that they can operate in, and it varies greatly from manufacturer to manufacturer and use to use. So train your guys on your specific equipment. If you have an off-road capable bucket truck and then you have one that's not capable, make sure that the people on the off-road one are trained specifically for that off-road vehicle as well as the other one. When we'll talk about palm pruning here real quick. This will be the last little section. Palms are pretty nasty trees for any of you guys down in Florida. I'm sure you already know these things. When you're removing the palm skirts, they can be very heavy. They can hang on there for years and years. There's all kinds of wildlife that likes to grow in them. Things are sharp, things are pointy. So avoid having to work underneath all that hanging stuff. Again, it's much better to use a bucket truck, or depending on where you are, you might be able to do all your work with long pole extensions. That might not be the case if you're working in Southern California, where you can have 80, 90, and 100-foot tall palm trees. Not going to be able to do those from the ground. Palms can be very difficult to access the very top of the palm tree. Palm frond edges can be quite sharp. Remember that I'm sure you've taken a rope and you've pulled on it and tried to cut it with a knife, and it's much easier to cut when the rope is under tension than when it's slack. If it's just a slack rope, you're going to have a very difficult time cutting through it. But these palm fronds, if you've got a tight climbing line, a tight safety line, it can easily cut through those things. Once a cut starts, then they lose efficiency rapidly. And there's also things like snakes and cockroaches and raccoons and squirrels and mean, nasty things in these trees. So all of that is a danger for palms. So that brings us to the end of this section. And I think we promised everyone about a 5-minute break or so. So it looks like we could go to just a little after 8.
So everybody,
whatever your time is there.
Come back at, now you got me confused, 10:01. Everybody come back at 10:01 Eastern time, but it's 5 minutes no matter where you're at.
Yeah.
Okay.
We've got a couple of questions up here.
Yeah. Do you want to do that before the break?
Yeah. So really, there's just 2 angles to be worried about: the 70 and the 45. So it's not too much out of hand. So but you probably will. They're not going to try to trick you with these angles, I don't think. Just know that the open face is the 70 and the other ones are 45. The other question here is explain time-weighted average. So time-weighted average is how they calculate sound exposure. So it's a certain level of intensity for a certain period of time. In the insurance industry, they have these little meters and they are time-weighted average meters. And so they clip one of these things to, say, your groundman's belt. And so the groundman might be walking back and forth from the trees to the chipper. So all day, as closer he gets to the chipper, it'll accumulate a lot of sound. When he's by the tree, maybe not so much. But by the end of the day, you want to be under a certain time-weighted average to get by not having hearing protection on. So it's just a way to calculate how much sound you're exposed to over the period of the workday.
Awesome. Thank you. Did that answer everybody's question? All right. Let's go on our break and we'll say be back in 5 minutes. So at 10:03 Eastern time. And I'll give you all a verbal announcement as well. All right. See y'all in a minute. All right, everybody, we got about 20 seconds, and then I'm going to hand it back over to Rob to get started. Everybody in earshot of their desk, if y'all can make it your way back. All righty, off to you, Rob.
All right. Everything sound good, look good. You're seeing what you're supposed to see.
Yep, I see the chapter 16.
All right. So we're going to talk about climbing and actual working in the tree part. Here, like I said before, this stuff's going to be pretty elementary. Climbing has advanced a lot. It has outpaced the documentation that we have in our study guides, but this stuff is still approved. It's still working. Just think about the basics when it comes to taking this exam. We're going to talk about the standards and safety regulations that apply to actually working in the trees, the safety equipment, ropes, knots, and tools, tree climbing techniques and safety hazards, principles of rigging, rigging equipment and techniques, and emergency response procedures. These things can be very difficult to understand if you've never seen them in real person. I strongly suggest that you find a tree care company that's willing to have you come out and be an observer. They're going to ask you to wear your PPEs because you're going to be someone there involved in tree care operations. So you'll have to have a hard hat and hearing protection and eye protection and appropriate clothing, all that sort of thing. But it's very difficult to visualize these things just from the text and the drawings and the pictures. You need to see it actually working and doing something so that you can better understand it. As far as these ropes, knots, and tools go, especially the knots, practice tying a few of them to help you understand them. So experience plays a big part. This exam used to be designed to where if you didn't climb trees or you didn't work in trees, you weren't going to pass it. But then there became a higher and higher demand for urban forestry. So people that are government interface types, and so they've backed off on that a little bit. You still need the experience in order to sit for the exam, however. Here's a guy that sort of looks like he knows what he's doing. He's got his cool rock climbing helmet on. He's got his long pants on. Looks like he's wearing boots. He's got gloves on. He's got lots of different colored ropes going in the tree stuff. And his saddle looks all cool and his carabiners. But he's really doing all kinds of stuff wrong here. And I'm sure there's guys out there that are climbers that knows what he's doing wrong. But he's using this chainsaw right here, going straight towards his leg. He's trying to hold this branch up, which would be a quite heavy branch to hold with one hand. So he's trying to control it that way. He's not using his safety lanyard anywhere. His knees are bent on both sides, so he's not really standing here either. So his only point of attachment would be the branch that he's cutting off and his rope that he's tied to on top of the tree. Can't really tell if he's wearing his safety protection. We don't see any ear protection going. So there is quite a bit going wrong here. So just looking cool doesn't mean you're doing it right. Unlike this guy that doesn't look very cool, but he's doing it all right. Uh, so here we've got a guy that has his appropriate hard hat on. He has the face shield and eye protection. And of course, he's sporting the really cool stash in here that identifies him as a He-Man tree climber. He has the ear muff types of hearing protection on the side. He's wearing non-gauntlet style gloves, a long sleeve shirt showing everybody he's a member of the ISA. He has on his leg chaps that looks like they've never worked a day in their life, and he's got these heavy duty boots on, which he should also have. He has his professional saw with all the appropriate safety features still intact. The equipment that you use, your life depends on it. So be sure that you are using safe, sturdy, clean equipment. So inspect it before each use. Every day when you get into the tree, Start your morning off during your job briefing by having everyone check their equipment. Remind the other people on your team that they too need to check the equipment. Climbing saddles should be checked for excessive wear and to see that the stitching and the rivets are strong and intact. Snaps. So this is a picture of a snap. Other things like carabiners and stuff like that. This is a snap. So it's got an eye in one end, and then it has a gate and a hook. So this would attach to another ring such as this, or it could attach to a rope. Normally it's going to attach, this end will be attached to the rope, and this end will be attached to one of the D rings. This is an approved snap. So it has, this is spring loaded, and this part is spring loaded, and it takes two things to happen here before you can open it. I'm not sure where my mouse has gone now, but anyway, so you have to squeeze the backside of the carabiner here to get to the gate. And then the part that's where the hook is, that gold anodized piece, that's the gate. So the piece on the backside is the safety. So you have to compress the safety in order to relieve the lock that's on the gate. And if you have it in the open position, you're holding it there, and if you let it go, it should be self-closing and self-locking. So it should go all the way back to its fully closed position, and the safety should establish itself on its own. So it's self-closing and self-locking. Here we go. Now I have it back. So this is the safety side over here. So this has to be compressed inwards in order to open up this piece, the gate. There are climbing carabiners. So this is an example of a climbing carabiner. So this one has this anodized aluminum barrel, and that barrel has to rotate until these U-shapes there and there line up with the gate. And then you're going to have to pull it down. So you're going to have to twist and pull to unlock it. And then that will allow this gate to open. But if you just let the carabiner go and do nothing with it, it should close by itself, and the barrel should rotate by itself and lock into position. In this position, the outside of this barrel hits a locking mechanism on the carabiner itself and won't allow it to open. So it is self-closing and self-locking. So it has that double action. So if at any point the equipment doesn't do that on its own, you can't just let it go. It might close but not lock. It's time to retire that piece of equipment and buy a new one. The climbing line or lanyard must be self-closing and self-locking. So here's an example of the end. So if it's built into the piece, again, it still has to be self-closing and self-locking. And this is the carabiner again, so it has to be a positive lock and a positive close. Both must have the tensile strength of 5,000 pounds. So tensile strength means that you can put it under that amount of weight before it permanently deforms the carabiner or the snap. So tensile strength is basically when it breaks, but not necessarily. But climbing lines must be at least 1/2 inch in diameter, or their metric equivalent, I think, is 11 millimeters. I'm sure somebody will correct me if I'm wrong. So it's 11 millimeters or 1/2 inch diameter is what you're allowed to climb on. Climbing lines should be just that, only a climbing line. Don't lower things with your climbing line. Don't tie things down to the truck with your climbing line. Your climbing line should only be used for climbing. That's going to keep it in a safe, working, and clean state. The tensile strength of these ropes needs to be 5,400 pounds. So why do you think that the carabiner only has to be 5,000, but your rope has to be 5,400? You're going to tie a knot in your rope in order to attach it to a carabiner or to a snap. When you tie into it, it loses strength. And so your rope has to be stronger than the carabiner so that when you are tying knots into it, or you're getting a bend radius on it that is too great for the 1/2 inch rope, in other words, you kink the rope, all those things lessen the tensile strength of the actual rope. So that's why you want your rope stronger than your snap. Your work positioning lanyards, these are ropes or straps designed to aid in climbing and tree work. Can be a means of secondary attachment to the tree. So not only are you attached with your climbing line, but you might also be attached with your lanyard. Lanyards are used in lots of situations. For instance, over here in the picture, this might be a chainsaw lanyard. So this loop might be attached to your saddle, and this end might be attached to your chainsaw tether. And so this whole piece, notice it has this little squiggly stuff in it. The fall protection looks similar, except the fall protection won't have this simple little snap on it. It'll have a true snap or a climbing carabiner at this end of it. But what this scrunchy stuff does is that if you accidentally drop it, or it gets stuck in a log and pulled away from you, the stitching pulls apart, and it'll act more like a bungee, so it'll absorb some of the shock, so it doesn't instantaneously transfer the shock to the climber. Every rope has its use. So we used to use 3-strand rope when I first started climbing in 1989. We indeed used 3-strand rope to climb with at that time, though they were just coming out with this Kern Mental stuff. The 16-strand rope over here was just coming online to the regular tree care guy. But since I was the low man on the totem pole, I get to start with 3-strand. It had relatively low strength, meaning that in order to get that 5,400 pounds of tensile strength, it had to be larger in diameter than 1/2 inch. Then we moved into inorganic fibers, all these sorts of things. And so we got down to these 1/2 inch climbing lines that you see pictured. And all of these have their own checks and minuses, their pluses and minuses. This is the one that I use, this one in the center. It's called Safety Blue. Inside of it, it has these little blue fibers in it. So if you chip away at the cover and you pull any of these blue fibers out, you've deformed that rope or cut into that rope, or to the point where you've jeopardized and it no longer has that 5,400 pounds of strength. And so you can either cut that section of rope off or retire that rope completely to do something else, either landfill or do something outside of tree care with it. Make sure it doesn't wind up on your trucks as a lowering line or something like that. Kern Mental just means that it has a core with a cover over the core. So you can see how these are white on the inside, and then it has the fancy stuff on the outside. So these are Kern Mental with a cover over it. Use the correct type of rope for the application. 1/2 inch climbing line is what we use for climbing. If you're lowering very large logs, you might want to use something that's larger in diameter than a 1/2 inch. You can go all the way up. I'm sure you've seen those big hawsers that boats use. So rope can get quite large in diameter, and it's specific for an amount of weight. So tensile strength is the maximum load the rope will support. If you exceed that, the rope basically breaks. A design factor or safety factor for arborist rigging should be a factor of 10 or greater. So what does this mean? It means that we want to not, if it holds 1,000 pounds, we don't want to put more than 100 pounds on it. It's basically what it's saying, so that you're giving yourself all that extra room in there for safety. You don't have a climber that weighs 5,000 pounds, right? So you don't want to put more than 10% of here, which would be 10% would just be 500. So you don't want to apply more than 500 pounds to the total system. And you say there's no such thing as a 500-pound climber. But when you start to apply forces other than just hanging straight down on it, if you're just hanging straight down on it, you might have a 200-pound climber with 20, 30 pounds of gear with him, and you still say, well, that's not very much. But then as you begin to walk out on a limb, or you're pushing against a branch or something like that, you could more than double your effective weight. So you could easily put 500 pounds on there if you weren't stopping to think about what you're doing. But that's what that working load limit is designed for. And why would you need a formula to do it when we know what it is for climbing? Because you're going to use you'll use ropes in rigging. And like I said, ropes come in all these different diameters. And so you might have 3/4 inch rope. You could even have 1 inch rope, and you'll use gear that goes with the 1 inch rope. Make sure that your whole system, you can calculate how much wood you can lower given the diameter of the rope safely. And so that this working load limit here calculation will help you to determine that. So a knot is a general term for hitches and bends. So it's an all-inclusive term. A hitch or a bend are both knots, if that makes sense. A hitch is a type of knot used to secure a rope to another object, another rope, or the standing part of the same rope. So we climb on a hitch. A bend joins two rope ends together. So you can see here the sheet bend, and then here's a hitch. So we're going around something. This type of knot is referred to as a friction knot. So here you'll put some load on this end of it, and as you put a heavier and heavier weight here or here, notice that this is attached to the climber's saddle. So as the climber sets down, his weight is going to be on this rope, the red and white one, but it's going to be on the red and white one through this blue one. So this blue line is going to get pulled this way, which will tighten all these loops up. And the tighter that gets, the more it binds onto the rope going through it. So that's why it's called a friction knot. So it's just holding on there by friction. The harder you pull on this side of the blue line, the tighter this knot gets, and the more firmly it holds to the red and white one in the background. So this is a prusik loop. So you can just take a loop. It doesn't even have to be tied like this. It could just be a loop, and pass it inside of itself twice around a standing line. And all of a sudden you have a friction knot as a result. These can be used as you're climbing knot. It can be used in foot lock. You'll see many uses for the prusik loop. You might also use it in the back of your truck when you're tying things down to gain some holding force to tie things down to the bottom of your truck. So there's lots of uses for these hitches. The one pictured, this is a split tail. So this is a climbing system in which the climbing hitch is formed with a separate short length of rope. So you can so this is a single line. So this would be what they call SRT, single rope technique. So there's also a double line technique. But on a single line, this is how you're basically going to have to do it on a single line, is using a split tail. So this is a separate piece of rope. If it were a double line, you're basically going to take this single rope, it comes up, goes over a tree and back down. And on this side of it, you're going to tie back to the standing part. So the loose side will tie to the part with your weight on it. And then you'll be able to advance the rope that way. This is the double rope. So this is the part that's going to hold your body weight. This part goes all the way down to the ground, and there might be a pool of rope on the ground. So you're going to tie it off to your snap, and then with the tail that comes out of the snap, that's the part you're going to create your friction hitch over here. And notice there's a little figure 8 that's put in at the end. The figure 8 notch, this is a stopper hitch, a stopper knot, so that it won't go through these coils. So it's a safety backup. Some people also put another one in between here. So you're putting a little figure 8 in between your snap and where you begin your friction notch, your friction hitch, because in the case of aerial rescue, you might come up and sever this line so that someone on the ground can then bear the weight of the climber and you can lower them down to the ground. So by cutting it here, well, I don't want this end to come and unwrap through this snap. So if by putting another figure eight here, if I cut between the figure eight and the friction knot hitch, then when I cut through here, then that figure eight's going to pull closer to here and stop. And so that's another safety measure. So you'll want a figure eight here and a figure eight on that side as well. The old school way of doing this was this taut line hitch, and that's what this is the taut line hitch. It mimics very closely. It works the same way as this prusik does. There's also a Blake's hitch that can be used, the Blake's hitch, and there's variations of all these hitches now that are acceptable, and it comes down to the climber's choice. I still like using the taut line hitch, but the drawback to the taut line hitch is that it can get really tight. So occasionally I have to stop and loosen it up so that it'll slide through the rope effectively. The Blake's hitch, because it's a little bit bigger of a hitch, doesn't have that same problem. So it remains easy to use from start to finish. But like I said, everyone has their own preferences for these things. Here's a guy up in a tree. He's got foot gear on, but it's not attached to the rope at this point. He's got his climbing system. He might be coming back down the tree. But the way that these notches work, again, this friction notch, the more weight you put on this side of it, the tighter it binds. However, when you're going up, you want it to loosen up. You have to take the load off of this part and push up on the bottom of that loop at the same time. So you might pull the rope and your knot towards you, put your hand on the bottom side of your knot and advance it, and then that's going to hold your weight. So you might, ever how far that is that you pull up and advance your knot. In single rope technique, you're going to go, that's how high you're going to go. In double line technique, you're going to go half that distance because it's going up and over and coming back down. The single rope technique is a lot faster. There's more control to it. Also, when you're ascending, the rope can go through ascenders that are on your feet. And they also have a type that goes on your knee. So you've got one on your knee on one foot, one on the boot on the other side. And so you can actually just walk up a tree like this. It's a pretty cool looking thing. We do use lots of knots in our industry, so it's good to go over the knots that you have in your text and make sure when to use what knot. There's the Swabish notch, the distal hitch, the Valtendane notch, the Blake's hitch, the taut line hitch, the prusik hitch, the climb heist, the prusik 4-coil, the prusik 6-coil. So there's all types of these notches, hitches out there. And then you also have all the knots, such as the bowline on a bite, the bunt line, the running bowline, the fisherman's notch, clinching notches. So just be familiar with the basic ones. Things like the Stilson hitch and the timber hitch. The timber hitch is an important one. The bowline's an important one. The running bowline is an important one. And then understanding how the friction hitches work. Those are the really important ones. You don't have to know or get down into the details of all these other types of knots out there. You don't have to know so much about the fisherman's knot or the double fisherman's notch or any of these crazy things. Just drill down on the ones that you'll actually use. Again, when you go out to apprentice with somebody or observe them in the field, take a look at the notches and the hitches that they're using and ask them how they work and if you can tie a few of them, if they'll give you a piece of rope. So one of the uses of cutting up your climbing line is to make training pieces out of. Hopefully they'll have some spare pieces around.
Rob, I don't know if you need to reword. Somebody's asking, will the knots be on the test? These knots that you had pulled up.
So the primary knots that we showed will be on the exam. So you might not see all of these particular things on there, but you will see a prusik. You might see a sheep's bin. You might see the taut line hitch, the Blake's hitch, and the prusik are probably what you're going to see. You'll also see maybe a slip knot. So just you're going to understand it more if you go out and you work with a tree care crew, and you'll see what the common knots are, and it'll become evident without much experience at all. Hopefully that helps. And tying them yourself helps you to understand how they work. And there are YouTube videos out there for all of this stuff. And I always say, check your source on the YouTube videos. Make sure that you're watching an accredited video, either from TCI or ISA, or you're one of the leading training companies. All have these short videos out there that teach you how to tie these knots. They'll even show you climbers and how the different climbing systems work. So if you don't have the opportunity to get a mentorship with somebody, at least look at them all on YouTube or some other video source. A lot of the manufacturers will also have videos. Steel has some pretty good videos. Husqvarna has good videos, especially about notches and felling and things like that. So try to get as many sources or different viewpoints as you can on these topics. We're often asked, how are you going to get a climber up into that tree if you're not wearing spikes? Because remember, we only wear spikes for removals. We don't want to wear them when we're just doing climbing activity. So we use a weighted line. So this is a throw ball. So we have some very durable line here. We have a bag that has lead shot in it. It has a little ring on it. So we're going to tie the string onto this ring. And this is a throw ball bag. So once you use it once, your string will never look like this again. It becomes this jumble of stuff, and you want to keep it as organized as you can. It doesn't necessarily have to be perfect looking, because sometimes chaos is just as good as wrapping it around something. But you don't want to introduce twists or memory into this throw line. So by using a throw bag or a stuff sack, you can just stuff the line into the sack, and it'll come back out just about as neatly as you put it in most of the time. So you take this weighted line, and you can swing it and you can throw it up into the tree, and then you tie your climbing line onto the end of this yellow string, and you can pull that into the tree, and then you've set your equipment into the tree without having to use spikes, and you've put it in hopefully at a good central working location. To enter the tree, like I said before, the ascending, so you can pull down on the rope, push up on the knot. But you can imagine that your forearms are going to wear out in a hurry doing it that way if you're absorbing all of your body weight every time you're using it. So you use a technique called the body thrust. And again, you can find videos for these, but for the body thrust, you're putting your knees or your feet onto the trunk of the tree, squeezing it and throwing your hips up into the air. So as you throw your hips up into the air, you have a real short period of time where there's no weight on your climbing line. And so when you throw your hips up, you take up all the slack in the climbing line and advance your knot, and then that'll lock you at that height. The other method is pictured here. This is the foot lock method. And this allows you to use your feet. So you could just climb up this standing line without having to put your feet on the tree or your knees on the tree. You can go up just as easily hanging or suspended over thin air. Other ways to enter the trees are climbing spurs or ladders. And really, there's only two reasons to wear climbing spurs into the tree or spikes. One is to do a tree removal, and the other might be an aerial rescue. So a person's life is worth more than the tree is. So if you have to use spikes to get up to the injured person in the tree, feel free to do. Ladders, you don't see a whole lot of people use ladders anymore, but for smaller pruning jobs, you might use orchard ladders. These ladders that are 15 or 20 feet tall, tripod type ladders that you're working around trees in. But they did at one point actually use ladders in the trees themselves. I think it's either, I think it's Davy, but I'm not positive. If you go to one of the tree care conferences, they have this old picture and it shows 15 guys in this giant elm tree, and you'll see ladders strapped to that tree all over. So it's sort of a deprecated use of the ladder, but it's still an acceptable means of getting in, but it's not too safe. Now we'll talk a little about the equipment, or quickly we'll talk about the equipment. You remember, you want to have good, clean, sharp equipment. You want it in a new, dry, clean condition. You want to have your safety, all the safety features in place, like the scabbard. So whenever you're not using, your saw goes back into the scabbard so that you reduce the risk of these teeth coming into contact with your climbing line while your body weight's supported on it. Make sure that your chainsaw has solid chain brake, everything's in place to remain safe. Any chainsaw that weighs, so just a quick to introduce this, but any chainsaw that weighs 15 pounds or greater than 15 pounds has to have a separate line that when you let go of it drops below your feet. So if you accidentally drop your chainsaw while it's running, it's not going to swing back into, like I showed that lanyard a while ago. The lanyard had all that scrunchy stuff in it. So your chainsaw lanyard needs to be long enough to where if you drop the saw, it goes below your feet. See, make sure that you're using bypass style pruners and you're not using anvil pruners to work with. Rigging. So again, the rigging is the use of ropes and other equipment to take down trees or remove limbs. A rigging point is the place in the tree that the load line passes through to control limb removal. So if I had, see if I can get my pen to work this time. So if I have a branch if I have a trunk that comes up and there's a branch that comes out here and goes back to the trunk and keeps going up. If I take my line and take my climbing line and come up and around this branch in this crotch, this point right here becomes the rigging point. So I'm going to load one side of this line up with some weight, and this side might go all the way to the ground. So if we pretend like this spike over here is a branch, this piece might wrap around here. And so the load is going to be on this side. So this would be the load line and the rigging point. And you can see that it says down here, natural crotch and false crotch. So this is an example of a natural crotch. I'm using the tree itself to run my load line through. On a false crotch, a rope tool is attached to the branch or trunk of the tree with a block or pulley attached. So I might have around the tree, I might have attached a line coming all the way around the tree, and on that line I would have a pulley. So then this load line would run through. The pulley itself then becomes the rigging point. There are some lowering, so this is an example of a lowering device. These things are very handy to have. It allows you to take the load line and wrap the around this capstan and then this outfeed area. So the guy who's going to lower the branch or the chunk down to the ground is going to use this end of the rope. And the more wraps you put around this capstan, the more friction there'll be on the rope, and the larger weight you can have on the load line and still be able to handle it. So if you have a very light branch, you might not put any loops around this at all. But if you had something that was a couple 100 pounds, you might put 1 or 2 wraps. And if you had something that was approaching 400 or 500 pounds, you're going to put more wraps on it. This thing is strapped around the base of the tree. Very handy. This one is a more advanced one, and it actually has a ratchet mechanism in it. So you can see this rod laying on the ground. This is a solid piece of steel. It has a pointy end that goes through one of these holes and allows you to crank on this capstan. So you could actually pick a branch back up towards the rigging point doing this. And you say, why would I want to do that? Well, if I cut a branch and this branch lands into a branch below it, I might want to pull the back end of the branch up to get it like this and make it easier to lower to the ground. So there are reasons out there for wanting to pull it back up into the tree. So know the different parts of a pulley. Again, you might want to go to a YouTube video and look at some of these devices, call up shackles, screw links, and get good idea of what they are and how they work. But the shackle is the U-shaped fitting with a pin that runs through it. We'll see a picture in a minute. The screw links are connecting devices with a threaded closure mechanism used in rigging. So it looks like a section of chain, but where it comes back around, there's a little barrel here. So the top part usually has threads on it, bottom part a little barrel with threads on it. So you can close that chain link together. So that is a screw link. The pieces here, this whole piece forms a block. The sheave is the inner workings here, this pin that goes through the middle that the pulley actually rotates around. So the block is a pulley used in rigging. This particular block is probably more of a rescue or a personal use system more than it is something you would use in a lowering system or a rigging system, but you get the idea of the different parts involved. So these two pieces, you could clip them together with a locking carabiner or a screw link. You can hold these things together once you run your rope through this, and that would attach it to a sling. A rope sling is a section of rope, usually with at least one eye splice used to secure equipment to the tree sections in rigging operations. So it'll have, sometimes they're an eye like this and a long tail. And these come in handy because you can wrap it around the tree and then wrap it back around itself using a timber hitch or timberline hitch. Makes it to where you can do big trees with them or small trees with them and everything in between. You can also use looped webbing. It can also be used as a rope sling. So there's a number of types of things that you can use as a sling that each have their purpose. So I talked about the timber hitch. Here's an example of it. So this piece that you see the block attached to, so the block is attached here in this sort of the woven end of it. And then the rest of that tail goes around the tree. Then it would come up just around the block itself. And then you start wrapping it around its own tail. So once you get several wraps on, this thing becomes quite sturdy. So here's the use of a clove hitch and a half hitch. You might use these or slip knots to run equipment up into the tree, tie on pole saws, pole clips, tie on other climbing lines, attach chainsaws to be lifted up into the tree. So these are good attachment ones, the clove hitch and half hitch. This is what's called a running bowline. So this piece right here, the way that it's tied, this is the bowline. You've probably heard that old mnemonic where you create a little loop and the rabbit comes out of the hole, runs around the tree and goes back down into the hole. That's how you form this bowline. And if you tie the bowline around the other part of the line, like you see here, and then you pull on this line. So if you pull on this line, that's going to pull up on this part of the bowline, and it runs up the tree. So this one, because it's wrapped around itself, this one's referred to as a running bowline. You can also have a standing bowline, so it's just by itself, it's just a loop that you've put in it by itself. Some techniques here, again, look these things up, see how they work, see why you would choose to use this technique in each situation, and it'll help you to understand and answer test questions. A butt hitch is a method of lowering pieces when the rigging point is below the work. There's not a picture of butt hitching here, but if he were to rig this piece off of itself, so you're going to cut it here and then lower it down if this were the top of the tree, that would be where you would use a butt hitch. This is just a standard lowering piece. So we have the load line comes up, goes through the block, and the block's attached with that sling, comes back down. This aerial operator is attaching it to the top of this log. He'll come down and make the cut here. The guy on the ground's holding this weight, or it might be going to a porter wrap. So I pictured down here. So this is not the appropriate place to put a porter wrap, but this is what the porter wrap looks like. It's a miniature lowering device. So after he cuts this piece and it needs to be lowered to the ground, this guy can then, with one hand, hold the weight of this log, which is probably more than his own body weight, but he can do it with just a couple of fingers because of the friction around the porter wrap. He's going to bring it down. So would this be a landing zone or a drop zone? It's involved in rigging. It's coming down to where he wants it. So this is a landing zone. It's a controlled release of the log all the way down to the ground. Now, if this climber up here were just pitching these logs over, but putting them in the same place every time, that would be the drop zone. So it's more uncontrolled. But here they've got a high-end driveways, all kinds of high-end plant material. And so they want to do as little damage as possible. So they're going to control it all the way to the ground. So this is the example of the landing zone. Here is some other rigging techniques. They say like one of the most complex techniques an arborist can apply is the speed line. I think that things have gotten a lot more complicated since the writing of this material, but speed lines become very handy. You might attach this end somewhere close to your chipper. You might even put this line onto your chipper. And if you've ever done a zip line, you'll know that as you approach the end of the zip line where you're having to land on the platform, the way that they slow you down is that there's either it goes down and has to come back up a little bit. So the change in momentum from downward where you're speeding up to upward where you're slowing down, and then here's the ramp, so you might slow down and boom, you come to a stop right on the ramp instead of hitting the ramp. And so it's the slack in the line that causes it to do that. So here you might hold this line very tight against the chipper, allowing this pulley system to zip down or speed down this line. As it gets close to the chipper, you put some slack in it, and then it's going to touch the ground. And when it touches the ground, it slows down in a hurry. If you're a really good operator, you can slow it down and all the butts of the logs land on the infeed table of the chipper. And you're like, yay, score. And you didn't have to carry anything at all. So the rest of the parts that are involved here, so again, you have the actual speed line itself that you're using, the equipment to attach a branch. This is a sling. So this is a loop of webbing that I talked about a while ago. So you just wrap it around the branch a few times, then back through the loop and onto a carabiner. That carabiner attaches to, this is called a rigging plate. So you can see where there's multiple attachment points on this rigging plate. So I could bring down several branches all at one time if I were the climber up here. This purple line is the return line. So after this has come close to the chipper and you're through, the ground guy is going to take all these things off, release all of the slings, and then put the empty slings back on here, and then the climber can pull it back up to the tree where he's working and do it all over again. So they're cut, speed it down, gets close to the chipper, and return it and do it over and over. All right, so that brings us to the end of that section. You bet. All right, so we're going to this is our last section. This will be it. Chapter 12, Tree Assessment and Risk Management. We are going to do a very high level look, the proverbial 10,000 foot view of tree assessment and risk management. keeping in mind that once you are a certified arborist for a while, you want to go back and add probably the tree risk assessment qualification to your portfolio, the TRAQ. And going through that process, that's a fairly intensive 2.5 day workshop with a big exam at the end of that one also. And that will get you much more detail oriented around this type of work. But all arborists, once you become certified, you have some level of responsibility to your profession and to the general public. That's why we're going to cover it here, but just keep in mind that it does get much more in depth than just what we are presenting here today. Get my laser pointer back. Everybody, I guess we're seeing the right things here. So we'll talk, well, okay, good. So we'll talk about tree risk assessment procedures. We've talked already a lot about wood decay and compartmentalization of wood, what compartmentalizing decay means based on its species, what kind of strength loss the tree might see as a result of decay and response growth. We'll talk about the mitigation of risk, and then we'll wrap it up with the arborist's responsibility and duty as it pertains to this information. There's the Arborist Code of Ethics. I think there's even a question, 1 or 2 questions could pop up on your exam, and that's something we have not covered in any of these classes, so be sure to read through the Arborist Code of Ethics, which can be found on the ISA website. Be familiar with that. Just seeing the arborist responsibility and duty jogged my memory about it. So tree assessment and risk management are important roles of the professional arborist. Once you become a certified arborist, guess what? You are considered a professional arborist, regardless of how much time you've had in the industry or what your function is. Even if you're an ISA certified arborist that has done nothing but drag brush, you are considered to be an expert in the industry. Or if you're in wastewater management and someone in your department said, hey, we'll give you a raise if you become a certified arborist, you will still be considered a professional within the industry once you gain this designation. Risk assessment is the process of evaluating the likelihood and the consequences that a part or all of a tree will fail and cause damage or injury. So there's a lot packed into that sentence. So when we talk about the likelihood, that's some sort of rating level, like it's not likely at all, or hey, gee whiz, that's happening right now. A lot of what I do are tree inventories in my business. And so if I'm out doing an inventory, sometimes I find trees that are in an active state of failure over a building or over a Mercedes or something. And so if it's in an active state of failure, it has a high likelihood of failure. What are the consequences? That tree might fall on the car, or it might fall into the building, or fall onto a person walking under it. That would be the consequence. So it's likely that the part will fail, and that part of the tree, it could be a branch or it could be the whole tree. If it fails, the consequence is going to be some type of damage, or it could be injury to something that's alive. So the 3 factors of the basic assessment: the potential for the tree or part of the tree to fail, what conditions exist that may contribute to the failure. If you have a tree that's leaning and that lean is over a certain amount, there's a higher risk of failure. If it's a leaning red oak, if it's leaning more than 20 degrees, then it's going to have an increased risk of failure. So that lean is a condition that might exist that would contribute to that tree's failure. And then what will be damaged or injured in a failure? So we're gonna rate the potential of it to fail, the conditions that exist that can make it happen, and then what will the result be when it does fail. So those are the 3 basic assessments. Failure potential, this is what we mean by likelihood. How likely is it to happen that an entire tree or part of the tree will break and fall within a given period of time? Now, it's not always just break and fall. Sometimes you might have a branch that grows out towards an intersection and covers up a stop sign so that you can't see the stop sign. That's a huge risk. So the branch isn't falling, it's not going to hit anybody, but because it's covering up a stop sign, people might run the intersection, and the result would be a car crash or even a fatality. So if it's a busy road, that the likelihood that something that occurrence will happen will be there. Trees or their parts fail, in other words, the branch falls or the tree falls over when the load they experience exceeds their structural capacity. So it's just like that rope that holds 5,000 pounds. If it goes to, or the snap that holds 5,000 pounds, if you put 5,100 pounds of stress on it, it's going to break because you exceeded its structural capacity. So trees are living organisms. They change over time. They're very dynamic. There's lots of decay that comes in. There's reaction tissue that grows. They grow at different rates, and the conditions are different from tree to tree. The load that they, or their structural capacity, might change over the tree's lifetime. So as the decay gets worse and the tree gets larger in diameter, this structural capacity is reduced and the load is increased. So as you increase the load and reduce the structural capacity, you get closer to the point of failure. We also discussed things called targets, and this is what's going to be damaged when the part fails. So the target in my scenario a second ago would be covering up the stop sign. That's going to result in a car crash. So it's not the branch itself that's creating the problem, but it's the branch blocking the stop sign. So you can eliminate that high risk by pruning off the branch so that you can see the stop sign or moving the stop sign. But that's what's going to be created there. However, if we just thought about a big branch and this big branch hangs over your house and the branch looks like it's starting to break, or it's a pecan tree that's loaded down with pecans, you've had a drought year, maybe that pecan branch will pop off and fall on your house. Your house is the target. So it's property that could be damaged. Without a target, there is no risk. So if you have a tree that's out in the middle of the woods somewhere, unimproved property, there's very little target there. There might not be a target at all. So there's these couple of people out in California that they spend a lot of time thinking about how to assess the importance of a target. Dr. Clark and Nelda Matheny, they've written all these books about urban tree, the structure of urban trees, when they might fail and that sort of thing. And they look at stuff like, okay, there's a pathway, a jogging path in the middle of a national forest. How long is somebody in the target zone of a branch if that branch were to fail? So it might be a half a second, and it might experience 100 people a day. So that's over the total period of a day, that's less than 2 minutes of total exposure. So that's a really low value target because of the potential to hit something in that target zone. Because when there's nobody there, there's no target at all. So the target only exists for that 100 seconds a day or whatever. There are people out there that study all these things for us and help us to create these systems and these assessments. So the potential of the tree to fail must be taken into account based on its species, the condition of the trunk, the condition of the root system, branch attachments, defects, and history. The city of Atlanta struggles with these definitions all the time, and you can see why. It's not something that is super straightforward. You have to spend some time in the industry. I've been to a lot of hurricane sites and tornado sites and natural disasters, forest fires, mudslides. I've seen it all. And over time, I've seen when trees fail and when they don't, and that sort of thing. So it can be difficult to just, without experience, to say pecan trees fail, and therefore the potential of failure is high. You can't. The example I gave a minute ago was a fully loaded pecan tree after a drought in a high wind environment. That tree has potential to break a branch off, pretty high potential. So the species would be taken into account. If that were an oak tree, you wouldn't have the same amount of weight that you would have on the pecan. Uh, Oaks tend to have more taper and are sturdier trees. The conditions would be the drought conditions or decay of the branch or how the branch, if it's bifurcated and you have that very tight branch union. If there are naturally occurring defects in the tree, like it crooked around another branch growing this way and the two rub on each other, that would be a defect. And then another one that comes into play quite often is history. So a pecan tree that breaks off, that's loaded down with pecans, if it does it once, it was heavy, it was loaded down with pecans, it was drought, we had all these things, and so it happened once and we understand why. However, the following year, if it breaks off a branch and it does not have any pecans on it, and we had good rainfall that year, and it fell off, then we say, what's going on here? Why did this fail? It could be the shrinking and the swelling of the tissue. It could have been how the wood fibers inside, the number of ray cells, how the cambium, how effective the cambium is at doing its job. So there's a number of things on a level that you actually can't even see that can affect the structural integrity of the branch. And so over time, two or three occurrences, and now the tree has developed a history of failure. So a tree can become a high risk tree just from producing this history of failure. We know that in the city of Atlanta, water oaks can just pop a branch off for no apparent reason, no wind, just a big healthy branch will pop off. There's no defects in it. We know that is a species that's capable of doing that, but obviously they don't all do that, because that if they did, all old water oaks of the same size would be falling apart, and they don't. So that's what we mean by the development of history on the site. Structural defects, these are flaws, they're decay and other faults in the trunk and branches or the root collar of a tree, which may lead to failure. We can visually see that trees are hollow, or we can hear it when we hit them with a mallet. We can see conchs growing around the base of the tree, these mushrooms that would help us identify what the pathogen is. And if it's one that's a delignifier, we would know that tree's getting weaker and weaker the longer that pathogen is there. Then we also should be able to understand environmental conditions which may contribute to the failure. Things like the drought or a lot of rain, storms, high winds, lightning, construction. Construction is a tricky one because you might have done a lot of damage, and when you as the arborist are called out to do the assessment, you might not know that it's there. I'm involved in a lawsuit right now where a company went out to do some irrigation work, and they put in some irrigation heads, and then a couple of years later the trees go into decline and they die. And they had two consulting arborists that came out, not me, looked at the site and said, wow, this site's really too wet. It looks like they probably cut some roots when they put this irrigation system in. And so the fault is over irrigation. What those two arborists didn't see was what I did see, because I was employed by the company that put in the irrigation system, not by the owner of the tree. And I was able to see pre-installation, when the company first arrived, that they had cut through the root systems when they remodeled the house. So the landscape didn't actually even go in until a year after that was all finished, but the irrigation company had the foresight to take all these pictures so that they knew what they were working with, trying to see some of the infrastructure so they would know where wires and stuff like that were. But the point is, they had lots of pictures and they knew that something else had happened. And as soon as I saw those pictures, I'm like, well, that's why the tree died. They cut all the roots. So they cut 60% of the root system off. So yeah, the tree's going to die, and it's going to take it several years to die. And so it was just coincidental that they saw, that the other two arborists saw the site so wet. So remember when you're called out to look at things that it might be more complicated than just what, especially with things like construction, grade changes, and soil conditions. Risk management is the evaluation of trees for their potential to fail on some repetitive measures. So you might say, I'm going to go out every 2 years and do a risk assessment on this tree and evaluate that tree to see if that potential to fail has changed. Almost all trees pose a risk of failure because at some point a tree dies, begins to rot, and it falls over. So it's standing up. You have all this potential energy of the thing standing up, and it's at some point it's going to be changed into kinetic energy when it falls. So there is a potential there. The more mature the tree is, the greater the risk. So the bigger the tree is, the more stored potential energy is there, the more likely it is to have things like construction and irrigation and all that stuff around the base. The older it gets, the more likely it is to have decay pathogens that are out there that are wearing away at the structural integrity of the tree. And at some point they do die. So the older they get, the closer they get to death. So again, the older the tree, the greater the risk. There are 3 levels of the risk assessment process. Level 1 is a visual only. This is typically what is done by municipalities or power line people. It's looking at thousands of trees as responsibly as you can. And so this is a consulting arborist would rarely ever do a level 1 assessment. But a level 1 assessment might reveal that you would need the next layer. So visual ones would be if you're in your car, you're driving down the road and you're looking for things that are in power lines, or you're looking for branches that are blocking stop signs. They're things that you can see without having to get out, walk around the tree, and actually touch the tree. So that's a visual only assessment, level 1. If you see something that doesn't look quite right, or you might be called out by a homeowner to do assessments on a tree, so they want to know if their tree's safe, if their tree's sick, or all of that. And so you would be called on to do a level 2 assessment. You're actually going to touch the tree. You're going to measure it. You're going to inventory it. You're going to listen to the tree by thumping on it and listening for hollows. You're going to document as much as you can. So you might talk to the homeowner to find out the history. You're going to put a D-tape on the tree and measure it. By touching the tree, we mean you're going to walk all the way around it. You're not sitting in your vehicle. You're up close and personal. You might give it an inventory number. You might say, today I looked at one tree. It was a 39-inch red oak located in the front left yard, close to the street. Homeowner indicated they've only lived there for 2 years. In that 2-year period, they've done nothing to improve the landscape. However, last year, the city replaced the sidewalk. You might say things like that. This level 2 is also known as a visual tree assessment, or a VTA. So it's not visual only, but it incorporates all this other stuff. It's a much more thorough assessment. So the visual tree assessment, not visual only, but looking at it and assessing it, the VTA. Now, during your visual tree assessment, when you're thumping on it, you might hear, it sounds like it's a little hollow. I wonder if it's hollow. How can I quantify it? The city's not going to let me take this tree down or get a removal permit just because I think I hear something in there. They want some quantifiable evidence that there's significant hollow on the inside of that tree. So I might do something a little more advanced, a little more invasive. I might do resistograph testing or tomography, or I might have to put a climber up in the tree because this is something I can't do from the ground. I look up, I see a squirrel poking his head out 50 feet off the ground. I don't know if that squirrel is poking his head out of a little pocket of decay, or if there's a huge amount of decay and he's selling condominium space in there or something. You might have to climb it. So anything that's extraordinary, that's more than just looking at it, touching it from the ground, this is going to be a level 3. So level 3 includes level 2 assessments with the addition of something extraordinary like tomography. Tomography is using sound waves to gather a three-dimensional model of what the inside of the tree looks like. They take, there's a transmitter, so there's a pin that you use, and then you have all these receivers spaced around the tree. These are little transponders, and so you thump on the transmitter, and the sound wave propagates through the tree. It propagates at different speeds depending on the health and density of the wood, and so it's picked up at different times from all these other receivers, and then they use computer models to gather all that sound information and speed information that gives you this three-dimensional look. Tomographs equipment is expensive, but so is resistograph experience stuff. But the benefit of the tomography is it might give you a 10-foot a 10-foot tall three-dimensional observation of the trunk. Whereas the resistograph, this is a drill bit that, as it's mechanically and indexed, driven into the tree, so it has a precise speed and rate of forcing the drill bit into the tree, which translates into torque on the actual drill bit. So the more dense it is, the more torque the drill bit experiences. If there's a hole there, it might not experience any torque. It might just go straight through without any resistance. That level of torque is measured. It can be done digitally, so you're looking at it on a display, or it can be graphed one-to-one onto a piece of wax paper. But it only gives you information where you're putting that drill bit in. So the arborist has to decide. I think the worst place is maybe 6 feet off the ground. So you might have to get a ladder to use the resistograph at 6 feet off the ground. Or you might say it's at knee level, and so you're doing it at knee level. But you have to use some forethought here to decide where the worst case scenario is. I might say it's at 6 feet, but what if the worst case scenario is actually 10 feet off the ground? I didn't measure it in the right place. So there's lots of ambiguity that's still there using the resistograph. So the more experienced the arborist is and the more diligent that they are of truly trying to assess the worst case scenario, the better the resistograph is going to be. You can also find these two things on YouTube. Make sure that when you're putting in tomography or resistograph that you put in tree care, because both of these tools are used for other industries as well. So take a look at those and you can see how they work. So how does the visual tree assessment work? What are the things that you're looking for? Back during the plant healthcare section, I talked about looping around the tree, or the diagnostic portion, sorry, when we were looping around the tree in this Fibonacci sequence of decreasing numbers, so that you're going from the outside of the tree going towards the center of the tree like a snail shell. We're trying to take in all those things. You're going to do the same thing in the visual tree assessment. Examine the overall health and structure of the tree. So I'm going to start off at a distance. Is the green the same color green as everything around it, or is it slightly different? Does the shape make sense? Do I have something that has a real upright canopy, but there's nothing around it? It's like, well, why does it have an upright canopy? Maybe it used to be in the forest, they cut down the other trees, and so it still has this tight canopy. So it's going to have a different overall form. So you want to look at all these things, try not to jump to conclusions yet, just like in the diagnostic section. Just take down the information, collect as much of it as you can, so that by the end, you can look at the total amount of information and try to come up with an answer. Look for things like dieback, gaps, or discoloration in the crown. Is it equal all the way around? Do I have one kind of fading yellowish branch and the rest of the tree's green? Why is that one discolored? And so you might, as you spiral in, you might get closer and closer, and eventually you might see that branch broke. It might be storm damaged. Or you might look up and my canopy looks really good, but man, there's 10 feet of clear sky and I've got another mature tree right next to it. But if I look on the other side, The canopies of my two trees are touching each other. Why is there this gap? Did the whole tree fall over? Is it in the process of falling so that it opens a gap of space over here and compresses the two canopies on the downside? Look for things like that. But whenever you have a lean, look for the reaction wood or the response growth. Also look for uplifted or broken roots. So this uplifted area is going to be at the edge of the compression plate. So it's good to look right at the trunk, but also remember to go out 10 or 15 feet away from the trunk and look for heaved soil, look for broken or cracks in the soil or broken compression roots, that sort of thing. And if you look at the leans, measure the degree of lean and record it. Everybody's cell phone probably has a level app on it somewhere. And you can actually rig up like a 2x4 with a couple of nails in it, and your phone sits on those two nails, and do it in a place where you can build it such that you can zero it out. So you take this 2x4, stick it on the trunk of the tree, put your level app on it, and you get a very accurate level or angle of the tree using that method, and take a screenshot of it and save it with the report, something like that. Document. Branches that extend beyond the rest of the crown. So if I have a branch that's way up here and it's part of a rounded head, well, when it begins to fall, it could stick out from the rest of the canopy 5 or 6 feet. I was driving down the road not too many years ago, and I see this big branch sticking out from the rest of the canopy, and I'm like, man, that's pretty weird. So I got out of my truck and went over there and looked, and sure enough, it was a branch about this big around that had broken, but it hadn't started changing colors yet, but it was on its way down. Look for that trunk taper. Remember the pictures of the pine trees that were growing straight up, and they removed everything around it, so you have this tall, skinny pine tree that has very little taper. Remember, the less taper, the weaker that trunk becomes. Also look at the trunk itself, look at the root collar, look inside of the root zone, and then also document the defects. Is it bifurcated, trifurcated, quadrifurcated? Quadrificated. Look for these types of defects, write these things down. Is there included bark? How bad is it? Is there any active failure going on? Is something weird already happening? Look at the tree canopy. Is it symmetric or is it asymmetric? Is it bigger on one side than on the other side? Is it more dense on one side than on the other? Are there low-hanging branches that could hit somebody doing lawn maintenance, or somebody walking down the sidewalk, or a truck driving down the street? Look at the foliage condition. How much dieback is it? Are the leaves the normal size? Are you seeing yellowing or chlorosis? What's the crown structure like? Is it like a Bradford pear, or is it like a fig tree with a billion branches emanating from the ground? Or is it like a beech tree with nice, good branch spacing in it, or a white pine? Is it great looking, open branch attachments that are evenly spaced? The white pine's a great tree to look at. Are the major branches, are they codominant stems? Are they broken limbs or hanging branches? Whenever you see these bifurcations in the trunks, don't just look at the trunks. Branches can bifurcate as well out on the tree, and it usually this tight branching habit is usually a genetic thing, and you'll see it replicate throughout the canopy. So if you see it in one place, step back and look at it and look for the patterns up in the canopy to see if you have codominant issues occurring up in the canopy. Because sometimes the failures on those old water oaks that I talked about are because of this tight branch or little to no branch spacing around. As a result, when they each grow in diameter, the pressure pops one of them off. So it's not the whole trunk. It could just be a branch that's doing it. Look on the bark of the branches and on the trunk. Make sure it's firmly attached. Thump on it a bit. Make sure you're not hearing separation. With that major freeze that we had here several years back, we had a lot of bark delamination where the bark cambium froze, but the vascular cambium did not. And so the bark separated from the cambium, and underneath the vascular cambium actually started to make new bark under it. And so now when you tap on them, you hear this ticking sound that you know the bark is loose. So you might bang on it for a while and it pops off, and then you see all this reaction growth underneath it that's been occurring. So thump around on it, look for these cracks and these splits, look for excessive leans. And again, excessive lean can be based on species. I'm not too worried about live oaks that are almost horizontal, but if it were a red oak in that same condition, I'd be really worried. We talked about looking for the reaction wood. So if it's leaning and it's growing towards the sun, like over a lake or something, it's going to have a more oval shape to it. So we'll know that it's had some reaction wood around it. Look for decay cavities. How extensive are the cavities? If you can measure them and record them. Pictures are cheap now, so take pictures of all this stuff as you're documenting it. Look at the roots and root flares again. Look for these conchs. Look for rot. Look for heavy soil compaction, things that can lead to advanced decay. Rotted, dead, or decayed limbs. You might have the bole of the tree might be undergoing the same sort of thing, as well as the root system. So again, look pretty closely at those areas. Look for cracks or splits on the trunk or the major branches. Cracks most often happen in the direction of growth. However, they can occasionally happen horizontally. Any horizontal crack in a tree is considered to be at high risk for failure, so closely examine any of the horizontal cracks you might see. Look for mistletoe in the tree, signs of fungal problems on the leaves and the branches, that sort of thing. What's the history of lightning strikes? What's the prevalent wind? From which direction is it? How strong is it usually? Look for past storm damage. Again, like around here, I'm always looking for this freeze damage now. Look for insect infestations. Look for ash trees. You're going to be looking for that emerald ash borer. If around here, if you're looking at live oaks or red oaks, you're going to be thinking about oak wilt or bacterial leaf scorch. Look for infestations that are out of normal. Improper pruning, epicormic branching. Was the tree lion's tailed? We talked about how horrible lion's tailing was for the structure of the tree. So document the fact it looks like it has been over pruned. It's been lion's tailed. You can also, from the epicormic growth that comes back, sometimes you can even tell when they did it. You might be able to look at how many nodes are on the epicormic growth. And I do this all the time, and the homeowners think it's magic, but I can say, it looks like you had it pruned about 7 years ago. Is that right? And they say, well, matter of fact, it is, because I counted 7 nodes while we were standing there on the epicormic shoots. But I might see one that has 14 nodes on it, one that has 7, and one that has 4. And so I might say, you've had this done several times, haven't you? And they say, yeah, we have. Every time they come back and they clean most of this interior out. So it's lines tailed over and over again. So look for that type of history. Ask those questions of the homeowners. Is the tree too close to the roadway? I did an environmental impact study of the linear park system in Ponce de Leon in Atlanta. And these parks were designed by Frederick Law Olmsted, but he designed them way back in time when the roads were much more narrow than they are now. There are not so many lanes. And so as they have widened the road, the trees get closer and closer to the curb. Even though the trees haven't moved, the curb keeps getting closer and closer. You'll also notice that all those trees have been hit by cars or mirrors. And I keep trying to talk them into going with Olmsted's thought that when you plant new trees, plant them further away from the curb, but they keep wanting to plant them back in the exact same spot when they die. Visual tree assessment, also this line of sight obstruction by vegetation. In other words, blocking a stop sign, or maybe you're creating an unsafe area where somebody might be hiding and could jump out and mug you. Things like that could all be part of your risk assessment. We've beaten branch structure to death, so by now you guys should be able to identify proper branch attachment versus this included bark business over here. Looks like we have a question that popped up. So the answer to the question is, can horizontal cracks in thick or corky bark be caused by compression forces, and are horizontal cracks in corky bark signs of potential hazard? Not necessarily, because the bark itself is splitting, so which you would need to examine a little closer. So if you see that the bark has these horizontal breaks in it, get a little closer to it and look and see if the rest of the vascular cambium is still in good shape, or if there's even sometimes new bark will already be in the bottom of those horizontal cracks on branches or on trunks. So see if you can look for a reason why. It doesn't mean that it's at risk for failure, but it's still an indication you need to look a little closer. So try to answer that question. Hopefully that gives you an answer there. So again, on the
Thanks,
branch
Rob.
structure, you bet. So you should know by now that this is a much weaker version than this for branch structure. So document the type of structure that you see. Here's a great example of branch taper or trunk taper. These do not change. You can look at this one. This does not change in diameter very much from top to bottom, but the wind forces here are shared with all of these trees, so they don't have to have a lot of taper. But if I was building a backyard and my house is going to be, right here in the foreground somewhere, and I want this one in my backyard, so I clear out all these other trees. Now suddenly this tree is exposed to forces that it never had to deal with before. It used to be able to share them. Now they're all isolated. So there's a much, much greater chance of failure if you expose these. Again, we'll talk about this response growth, this reaction wood. If you look at this tree, it's growing out over the lake, and then you see how the trunk starts to grow more upright. So once it gets out over the water, the adjacent tree here can't really get to it before this one does. So this one grows out over the water to find the sunlight. Then once it's out in the clear, it starts growing straight up once it's out from the shadow of this other adjacent tree. So if I saw this, I'm thinking this makes sense. It's growing out over the lake. Once it gets there, it goes up. But I need to check it. It might, from here to here, might be 36 inches. But then when I walk around it and I'm standing on this side of the tree looking at it from this angle, it might be much more narrow. So like in that short video that I played in my last session, remember it looked pretty thick on one side. And then as I walked under it, I saw that it was only about this wide, but from the side, it looked like this. So that's telling me that it's reacting to its situation. It is growing wood in response to that gravitational stress. So that means this tree is pretty darn strong. But then you look at this one, and this trunk is nice and round. You could walk around it, and it's nice and round. And then something else looks funny here. Why is all this grass green? Maybe as it's compressing on this side, it's lifting up on this side, and we can see that it has an angle to it. It looks like the tree is shifting, so it's aerating the soil over here, which turns the grass green. And we also notice a difference in colors here. So over here, you can see a difference in color between sidewalks. So maybe it's a question to ask, was this replaced? Another thing to ask over here, you can see this little section. It looks like it might have been replaced. Did they open a trench up here and install a new water line or a new irrigation line or a new gas line? It's something here that would have cut through those roots. These are all clues to figuring out why this tree has a lean on it. So if we were to cut a branch open and look at it, so branches we're hoping come off horizontal. This would be the bottom side, this is the top side. So this is where the tension wood is formed, and this is where compression wood is formed. In general, hardwoods are said to produce tension wood as a reaction to gravity. So it's going to build up density on the tissue on the top side to make it stronger. Wood's already pretty strong in tensile strength, so it just has to add a little bit on the top side. And so the density of the wood increases on the top side if it's a hardwood. On conifers, the conifer reaction is to produce compression wood. So you can see how it goes around and then has a little tear shape. And then that tear shape on this bottom side gets more and more exaggerated, almost to the point where it has like a little point to it, until This is the biological center of this branch. And so you can see that it's much more towards the top than it is towards the bottom, so it's produced more wood. Now, I'm sure there's university guys that have studied this, but I look at them and it looks pretty much the same to me. This one had a lot of growth here. The growth increment you can see is much bigger here than the same growth increment here. But in the case of a hardwood, remember that there's more tissue here than there would have been if it were growing straight up and down. So the more straight up and down the tree is, the closer the biological center of the branch is to the physical center of the circle. But for the test, keep in mind, hardwoods produce excessive tension wood under reaction, and conifers produce compression wood under gravitational reaction. We also have the compartmentalization of decay in these trees. There are trees that are good compartmentalizers and trees that are not so good at compartmentalizing. You've got maples might not be the greatest compartmentalizers. Ashes are not the greatest compartmentalizers. Fig trees are not that great. Magnolias are not that great at compartmentalizing. These are trees that quickly, Virginia pines are not that great. See if I can get to it here. Trees that are pretty good, or most of the oak trees are pretty good at compartmentalizing. The elms are pretty good at compartmentalizing decay. So take into account this when you see something like this. Take into account with that decay, how much decay is there, and how rapidly it's accumulating. So back to this model where you can see that we have lots of wall 4 here. Wall 4 is pretty strong. It's totally encapsulated the decay area, but it appears that wall 2 totally failed. And we're just being isolated by wall 3, which are those ray cells that are catching it here. Watch for these cracks or splits in the trunk. This tree's obviously, it was bifurcated. It was a weak point of attachment. Now it's splitting all the way to the ground. Here's an area of depression. It's like, why is it doing that? Most likely this was caused by a clothesline or something like that wrapped around the trunk of the tree. So we see this sort of choke point. That's also going to be a weak part on the tree. Here's some older trees. This is one of the parks. This is a tree that was assessed by Matheny and Clark out in California. It's a big redwood. Here's a nature trail that goes right by the side of it. And they've still decided to leave this tree, that it's worth retaining for historical value. But it does have an enormous amount of decay. Here we can see another type branch union. We see some reaction tissue. We see where it's probably failed once before, but it didn't fail to the point where it cracked all the way off. It just broke open, and so created some reaction tissue in there. This is an old pruning wound. So this is from a climber's perspective, looking back down at the ground. And you might have had this U shape, but it had a sucker right in the middle of it. So you might have pruned that old sucker off. And so that little decay pocket occurred inside of there. Probably not the best choice to have left that. Some of them are difficult to assess if you're just driving down the road, but the more you do this, the more you will begin to recognize the signs that something's going on, that it's not quite right. There's a book out there called The Body Language of Trees. And so if you're going to get into these assessments, I highly recommend that you get this book, Body Language of Trees, because it goes into why the trees produce this reaction tissue in such a way, and how you can learn to recognize these growths that are associated with failure. This tree, this diameter of trunk, you would think, well, why is it so big down here at the base? So it's trying its darndest to grow reaction tissue to be strong enough to hold the tree up. So you'll notice this white part over here. So that's what's called the sound wood. And we look at a ratio of sound wood to decayed wood. And so the more decay there is, the less sound wood that there is. And you can, if you're thumping on the side of a tree, if it's a big tree, you can start to pick up the sound of hollowness at 6 or 7 inches of solid sound wood. So if you're thumping on it and it's obviously beating on a drum, you can hear that it's hollow. It's probably much less thickness than 6 or 7 inches. So on this tree, which was just a matter of about 3 or 4 inches, I could have easily have thumped on this with a rubber mallet and heard that there was a hollow. We could have done a resist graft test and proven that the shell wall was really thin all the way around, and probably could have taken care of this hazard before it fell and did property damage. But reaction tissue can cause seams to form, butt swell, asymmetry. In other words, the trunk won't be round. Also look for things like dead branch stubs, look for old wounds, and look for those cracks. Again, codominant stems are always going to be something to zoom in on and look to see if it's failing. The trees with multiple, this is a little linden, but it could have been a Bradford pear or something like that with its multiple branch attachments. We know that's bad also. Cracks or separations in the soil may indicate soil heaving from excessive movement of the roots, which can be a warning sign of failure, especially if the tree is leaning. Here's a couple of examples where construction had an impact. Notice this tree has fairly small leaves on it. We would expect them to have larger leaves if it had a nice intact root system. So it looks like they put in a new curb. You can also see two different colors of asphalt out here. So they might have dug all this up to put in the new curb, or they could have dug it up to replace a gas line, something like that. But this tree had limiting rooting space and might have had roots cut due to construction, and so it just falls over. This is not a very big disc of dirt that hangs out of here, so it could have had root decay, but also you see this sort of square box out here. Usually when you see these square boxes, they were trenching. So they were trenching out in the street, or maybe they needed to reconnect a sewer line or power line or gas line to the house, cutting through the root system of the pine tree. So be careful. Try to take in, again, as much information as you can and document. Some of these wounds are very meaningful. Some of them aren't so meaningful. Some of them will become meaningful. This is a canker. This is fusarium rust on a pine. And so this fusarium, that's what gives the older pines, fusarium begins to look like a cat face, or you see these, what looks like sunken bark on the tree. This is what they look like when they first got inoculated, just these fat, swollen areas. So this can become more dense wood. And so when the wind blows, the forces are transmitted around it. And so it could lead to trunk failure. Here's a trunk with old vascular tissue, and we see these horizontal cracks. So this is not bark tissue. This is actually in the vascular tissues cracking. So this would be a tree to think about removal on. It's obviously flexing enough to break this old tissue. The original wound was probably caused by someone hitting it with a car or something hitting some type of compression damage. Same thing with this one. It was probably hit by a car coming, or a truck coming out of the driveway. So eventually a tree like this would need to come out. You can see it's also bifurcated. So it's a bifurcated trunk, plus has all this internal injury. The injury is on the main trunk wood, and we know that if you injure trunk wood, the limit of decay can be the size of the trunk the incident occurred. Here's some more cankers on the trees. These cankers can be caused by fungi or insects or bacteria, but they can create weak spaces. Here's another fusarium rust on a pine. Excuse me. Here's some more swollen plant tissue on the outside. We might call this a gall. So galls can be initiated by mites, fungi, bacteria, and it can just be straight out cancerous occasion. But these can become weak spots in the tree, so they're not as strong as they would be otherwise. Here we have some other forms of abiotic damage. String trimmer damage is very popular in park systems where the grass grows all the way up to the trunk. This tree, not even sure why it's still alive because they paved all the way up to the edge, but by doing so, people have hit it with their vehicles time and time again. And remember when I said damage was over a period of time? If I went back out to this house, once the project was finished, the soil line's going to be up here just under these two little vents. And so the soil is going to have to taper coming out into the yards. And so when you taper that soil, it's going to bury the root systems of these two trees. It's even going to bury over half the root system of this one. So there could be a significant amount of root damage caused there. And notice where the silt fence is. The silt fence is over here where the tree conservation place should be. It's on the downhill side of the construction. So every time it rains, the silt's going to build up on top of these roots as well. A lot of bad stuff going on, but if I went out there today, you'd see shrubs and everything would look all happy and the trees would look bad. And you're like, man, what happened here? Take that history. Get the oral history from the homeowner. So as fungi digest wood, it decreases the strength, obviously. Fungi may or may not form fruiting bodies. So think about apples. On an apple tree does not have to produce apples to be an apple tree. So fungi do not have to put out reproductive structures in order to be destroying the tree. So just because it has one or two fruiting bodies, it could be an enormous amount of decay, or you might have decay and no fruiting bodies, or you could have a ton of fruiting bodies and just a little tiny pocket of decay. So all the fruiting bodies are is an indicator to look closer. We break rots into three categories: white rot, brown rot, and soft rots. White rot decays the lignin within and between the cell walls in the wood. Lignin gives wood its compressive strength and loss of stiffness. So something like armillaria or Ganoderma is going to get in there and munch away on this. The wood's going to become much more brittle. It's not going to be as flexible. Brown rot is most common on conifer trees and is the primary decay mechanism for cellulose, leaving behind the stiff lignin and reducing the bending strength. Soft rot is similar to brown rot as it degrades cellulose and has some characteristics of both white and brown rots. So where the rot occurs is also a good indicator. So you could have a white rot, basal rot, which means at the bottom of the tree, or heartwood rot. So if it's a heartwood rot, we know that it's rotting from the interior out. And you could have sapwood rot. If you've ever seen those little woody ear mushrooms growing up along a cherry tree or something like that, is a sapwood rot. It's following the sapwood. Decay can cause significant loss in strength. So just like we showed earlier, all this discolored wood is being rotted. There is a delignifier here and something munching away on the cellulose. And notice the shell wall thickness is just an inch or so thick. If the tree has 30 to 35% loss of sound wood to decay, action should be taken to remove the tree or the branch. So this one is obviously about 95% sound wood loss. So there's only about 5% of the live tissue left. So this is obviously one that should have come out. This 30 to 35%, the real number is 33%. If you have more than 33% structural strength loss in a tree, you should consider it for removal. And this is based on statistics that have been gathered around the world on trees that have failed. So trees that actually fell, they broke. People went out, took measurements of their diameter, and found the ratios of live wood to dead wood, and submitted it to the National Tree Failure Database. And it indicates that most trees that fail have 33% strength loss or more. There are trees that fail with 5% strength loss. There are trees that, like this one, that didn't fail until they reached 95% structural strength loss. So this 30 to 35% is just the thickest part of the bell curve when you look at the statistics. I know this is a long section, but we'll be through soon. Signs of internal decay, you might see it on the exterior and say, yep, there's decay. Another sign is going to be this decay conch, the fruiting structure. On this one, we have 3 trunks on here. It looks like there's some reaction tissue along this point of separation. And then at the bottom of it, we see this this discoloration on the wood. And that comes about from an internal infection. So there's probably decay in there. Investigation may be needed if you look up any decay higher in the canopy. Don't be scared to say, here's my level 2 assessment. We need to take this to a level 3 and have someone look at it. We can quantify the amount of decay using something like the resistograph, aerial inspections. Filling cavities does more harm than good. So in general, we do not fill cavities. It's unnecessary. Sometimes we want to look at the decay on the root system. Maybe the whole trunk looks fine, but there's something else going on. So you might do a root collar excavation. So this person's using an air spade to do just that. So they're removing the soil without doing trunk damage and looking under the soil, looking for things like these decay organisms or girdling roots or other pathogens at play. Resonance testing, this is just what it sounds like. You're taking a mallet, you're thumping on the side of the tree, and if you can hear it, then it's probably pretty hollow. You can also use a measuring stick or a probe inserted directly in through the opening of a cavity to take measurements. You can use an increment borer. This extracts a little core of wood, and you can examine like increasing or decreasing wood rings, or maybe there's only, you put it in 8 inches, but only pulled out 3 inches of wood. So there might be a cavity after that first 3 inches. So you can use decay detection devices. There is a hazard assessment form. Using these forms helps you to maintain consistency in your observations and in your recording. Be sure to record all your observations and measurements, predict some sort of hazard potential, and name your targets. Look for the maintenance history of the tree. Again, I talked about Matheny and Clark. Their book is a photographic guide to the evaluation of hazard trees in urban areas. That's where the track course is actually based off of this book, as well as some others. Mitigation is what you can do about it. Sometimes, like with the instance of the stop sign, you can prune the branch off and reveal the stop sign, and you've mitigated the hazard for the time being. So it could come back. That fact that it can come back is called residual risk, meaning that another 5 years it'll grow back and get in front of the sign again. But you could be just removing dead or dying branches. You could prune to reduce the weight, remove, you could subordinate prune to try to deal with codominant stem issues. You could move the target if the target's a parking space, close the parking space, or move a picnic table, or move the campsite, something like that, removing the target. You can install cables or braces. You can put in lightning protection. And remember, you'll have to continually monitor these things because it will change over time. So what is your liability as an arborist here, or as a owner of a tree? When a person has suffered injury or damages, liability must be identified. That means whose fault is it? Liability is based on cause. Causation means that the injury can be traced back to a defendant's action or lack of action. An action could have been a lion's tailed it year after year, eventually making it weak. And we know as an industry that this weakens it and increases the risk of failure. Or we saw that there's a dead tree and we failed to remove it and it fell on our neighbor. Liability does not account for unforeseen circumstances such as acts of God. Arborists must understand the responsibility and liability that accompany tree risk assessments because you have a duty of care as a certified arborist. Because arborists are considered experts in the tree care industry, they can be held to a higher standard for inspecting and recognizing hazards, even if they were hired for purposes other than a tree risk assessment. They're still going to hold you liable because you are on the site and you are a professional. Document all potential hazards. Negligence is the failure to exercise due care. This occurs when someone fails to perform their job duty, even though they realize that it's going to happen in the foreseeable future. Causation, in fact, means that the damage or injury or death can be traced back to someone's action or lack of action. Proximate cause, the injury has to be reasonably foreseeable. We can see that this dead branch is going to fall on this house over this person's bed. So there's proximate cause for removal. So, if you are a municipality, so you might have something like this in your documentation. Any tree inspections performed while our arborists are on site for any purpose will be considered a level 1 assessment per the ANSI A300 Part 9 standard and will only identify the most obvious defects or needs associated with tree defects. More thorough and documented assessments, level 2, can be performed for a fee upon request. So if you're even if you're a company and that someone hires you for or asks you for a quote, a removal quote, and you go out there and while you're there you see another dead tree in the backyard, you need to note that there was a tree in the backyard and ask them, do you want to do something about it? And if they say no, say, I asked the homeowner about it and they did not want to deal with it at this time. Something, just document it as much as you can. Don't ignore it. You can be held liable for those things as well. So by putting something like this in your quotes, it helps to isolate you from going to court somewhat. There is some vocabulary that's important to understand. Likelihood of failure, we use terms like imminent, probable, possible, or improbable. Impact, we would say high, medium, low, or very low. And then consequences, severe consequence, significant, minor, or negligible. These things are all tend to be pretty vague because we have to incorporate all the differences in species and circumstances and growing environments and all that sort of stuff. A live oak growing here in central Texas doesn't see the same forces that a hurricane would produce on the coast of Georgia. There's differences there. Can consider things like, or using the words like defect, load, response growth, risk rating, residual risk, and reinspection. Avoid using the term hazard. Hazard is a legal term, and once you use or associate the word hazard with a tree or tree situation, someone has to act to mitigate it, to change it from a hazard to some other designation. So remember that tree out in the woods is never going to be a hazard because it doesn't have a target. So by calling it a hazard, you've identified that there's a part that's going to fail, it's likely to fail, and there's a significant target. Finally, there's this act of God that I talked about a second ago, and this is an occurrence due to natural causes that could not have been prevented or foreseen by ordinary skill or foresight. All right, that brings us to the end of all the sessions.